but I'll make a start. My talk is going to be about what inspired me and how I got into broadcast engineering and where it's taken me and some of the technologies that I've been involved in. We can always have a discussion afterwards. It depends on how much time you want for your own presentations and your own discussions. But anyway, is it fair to say that most of you know who I am and you've had some contact with me before? Well, if you don't, obviously my name's Tim Amsdon. I am an associate professor at the university in the School of Electronic and Electrical Engineering. I'm also the Director of Industrial Relations. So what that means is behind the scenes, the university or our specific school has something called the Industrial Advisory Board, where we invite people from industry to be members of our board and to essentially look at our programs, the modules that we teach, and for them to say, this is a good idea, or maybe you could make improvements in certain areas, or maybe certain technologies should be covered, certain platforms, etc. That is the function of the IAB. So that's something you don't necessarily see happening, but you might be aware if you look at the TV screen down in the foyer, when it's rotating around, you'll actually see that there's some slides appear which show you which companies are actually involved in our industrial advisory boards. And we have many high-profile companies in there. So I lead that. I also, as some of you know, and I think you've been on trips already, I organize some of the trips and I work with Ben Chong. There's also guest speakers. Did anyone go to the Consult Red presentation on POCs, on proof of concepts? It was, yes. Did you go? Oh, yeah, I saw your face. I saw you there, Craig. So I also helped organize that, and Rahul's a friend of mine. I've actually worked at his consultancy business. It's not in my slides, but we can talk about that too. I forgot to put that in, actually. And I'm also the Deputy Director for Student Education, specifically on taught programs. Yes, do you have a question?
So, for industry and how to supervise the university's modules.
Yes.
And I saw you are associate professor. So are you one of the
members of the board? No, I'm dedicated. I'm a teacher. I work here in the university. I did work in industry, and we'll get to that in a moment. So I'll cover some of my industrial experience and how that relates to broadcast as well. So Deputy Director for Student Education, specifically on taught programs. So I'm overseeing the programs that you're obviously studying. I also work out the timetable. So if there's any problems or anyone wants to shoot me down about timetable, that's mine. But don't blame me for everything. It's not all my fault. Also, if you do want to contact me, don't be starting any, don't want any trouble causing in here. It's 17:01 and it's in the afternoon, 5 till 6. I know, I'm very aware of this, don't you worry. My office, if anyone would like to come and speak to me in person, is 2.63, but please book an appointment by email first. And if you want to email me, my email address is there as well. So that's everything I think you need to know about me. In terms of teaching, ELEC 5032, which you might do if you're doing an MEng program, you'll see me in your final year of MEng. That is modern industry practice, and I'll talk you through industry. Yes. Jodrell Bank or the other one? Is it Jodrell? Manchester way, over Manchester. Yep, we can speak. Well, we can speak about that afterwards. No problem. So ELEC 5032, which is modern industry practice, I teach that. That's an MSc MEng module. Also, I'll be teaching the new RF and microwave engineering module in, well, it'll be next year, 26-27. All right, but I'll cover that as well at the end if we've got time. So, as I said, this particular talk is not fixed entirely on broadcast standard. I'm not going to be talking about broadcast standards in great detail. There's no heavy theoretical stuff. I'm just going to give you what inspired me to become an engineer and where that started and what event that was. And you might even draw some comparisons to your own life and why you ended up doing an engineering degree. So it's at my life in broadcast. Where did it begin? Well, it begins when I am 9 years old, right back in 1981. And up until this point, I'd not really shown any interest in technological advancements. I was more interested in watching the cartoons on the screen of this old TV set here, which is a Philips G8 CRT-based television set, full of TV. So I'd spent most of my young life sitting in front, watching those images, listening to the sounds coming out of there, and not particularly interested in anything else other than that. Then something remarkable happened. My dad took the back off the TV set because there was a problem with it. And that opened up a whole new world. So this is the old test. This might not be, it might be a little bit grainy on here. You can always access the look afterwards. But this is what the old TV sets look like inside. Lots of discrete components, cams, wires everywhere. That is how a TV set from 1974, which had been in our house for almost 7 years, this is what it looked like. Just a mass of wires. And this fascinated me. I can remember the moment, 9 years old, and I thought to myself then, I want to know what's going on in there. Now, my dad did a fairly good job of explaining what each component was doing in terms of scanning a TV line to produce an image on the screen. He wasn't an engineer, but he had a pretty good idea. So he never trained, but he certainly knew his stuff, because years later I marveled at just how much he did know. So that's what triggered it. Of seeing all those parts. Yes, you had a question, Craig. Yes, there are effects. This is the actual choke here. And I know for the benefit of the people online, you can't see this, but maybe I can move them. Can you see if I move the mouse around? Can everyone see that? Hold on, I'll see if I can do it with the marker. I'm specifically talking about this area here. Can you see it now? This has got what we call the deflection coils in it. And what's happening in there is you have a line of TV information. It's analog TV, no digitization in this age. And it scans a horizontal line. And then it moves down a line and it scans another line. Now, I won't get into all the details, but it actually has fields which are set up with interlacing. Have you heard of interlacing before? You might have seen that even in digital platforms that enable you to set up pictures and video. You have an interlace, which is basically an odd and even field. And you scan the odd field, then you scan the even field, and it relies on something called persistence of vision. Have you heard of this? Persistence of vision. Our brain holds an image for a certain period of time, and it enables you to have a continuous flowing image without it flickering too much. But this was at 50 hertz, and it does flicker a little bit. However, that's the region that deflects that electron beam. Yes.
Sorry, about what they call interlacing.
Interlacing. Yes, you have different fields. Two fields make up one frame. The Americans, I think, they work it the other way. They talk about frames and then fields. But we have fields, and that made up a frame. So this is what controls the electron beam, the deflection coils. So you can see that there were lots of discrete components in there, separate transistors, lots of capacitors, inductors. They were expensive. They used high voltages, and they were potentially lethal because they had a voltage which was applied, what was called the final anode, which accelerates the electrons towards the screen, and that was operating at around 30 kV, 30,000 volts for a TV. So really, a young boy like myself had no business in the back of here, but from the age of 14, I was actually tinkering with these things. But I did learn quickly. The library used to have books that contained these things. You know what this is? It is from a service manual, but this is specifically a schematic circuit diagram. And this is the circuit diagram for a TV set, a Philips TV set from that era. I don't think it's a G8 specifically, but it is from that era, and you can see all the discrete components. Now, the wonderful thing about the old TV technology is that you could actually see directly the signal path for both the audio content and for the video content itself. You could see where the power supply circuits were. You could find all of this very easily using a schematic. Now, when you open a modern TV set, first of all, it doesn't rely on the scanning technique that we used in these early CRT or cathode ray-based TV sets. It uses a computer, which is basically modifying pixels on the screen. So it's not doing a traditional scanning technique. But this is all analog, and it is all happening in real time. There's no processing going on that's shifting things around. It's all in real time analog. Okay? Now I see these again from my father. He shows me these schematics. I have no idea initially what they mean. As I get older into my teens, I start reading. And this is why I'm a big advocate of reading. I know you like YouTube videos. I know you like just watching a snippet of something or maybe loading something into ChatGPT, but there is something beneficial about reading either papers, so these are research papers, or reading books. So these were the books that I started out with. This was my inspirational book, written by Gordon J. King. Way back in the 60s, he initially wrote this book, and it was a revelation. It enabled me to go from having a rudimentary understanding of what might be going on in the TV and being just curious and not really touching anything that I didn't know about, to comprehending and understanding what's going on and being able to make some informed decisions with some support from my father, who knew where the dangerous areas were. But I started reading books, and this was the first one. So I leapt from just seeing the inside of a TV to now seeing a circuit diagram TV, and making the leap then through theoretical work that had come into play from the books to starting to understand some of the concepts. So the concepts here, we're looking at a single line of TV content from an analog TV transmission, and we transmit this weird synchronization pulse. Does anyone know what that might be for then? A synchronization pulse. Yes.
To like mark the beginning of each frame.
It is the start. If we imagine us scanning this image here, you have a starting point. It tells me the starting point for that scan.
Yeah.
So start the line here and then scan across, and then I now have to do a field return, go back, start another line scan. That's what it's telling us. That's what the synchronization is for. Now, up until I think it was the late 60s, all TV transmissions were in monochrome, black and white. So there was not, this signal didn't exist then, and neither did all these color information. You just saw the step pattern, which gave you grayscale. So you have what we call peak white, and then black level here. And then there were certain porches, and you can read about it. So this is a little bit of history. That's how we used to do it. We used to scan line by line, build up these two interlaced frames, and we could recreate in a color system the color bars. So one line of this shows you the step. There's a monochrome element, and there is also what we call the chroma element as well. So color information and luma information to generate this image. Well, I was fascinated by this. This is incredible stuff. This here is a color burst, and that was used to synchronize the color information that's in the transmission to produce the right color or register on the screen. So this led me, when I'm reading about it, that I needed test equipment. And that piece of key test equipment was an oscilloscope. And I've shown you the kinds of scopes that I could afford back in the 1980s. Yes.
Yeah, so what is the start and the end of the interlacing, like this down house is this start?
You'd end up with this. This was a single line, but there is also frame information which I've not got on here. But you're welcome to do some more research on it. You can read about it in your own time. But we still have, even now, there are still some boxes, set-top boxes out there, receivers that have what we call a composite video output. It still exists, and you can still look at this composite with a composite video signal, which means you've got the chroma information, the luma information, and synchronization within that entire signal. It was a marvel of engineering. It was developed before computers. TV predates computers. There was no computer modeling. It was all done using slide rules, Smith charts. If you've done Smith charts yet, for the RF side, it was all done without the aid of computers. Even calculators didn't exist back then. Incredible. When you go read the history of chroma information and how that was included in an existing system, it's even more miraculous how this was achieved. So this is inspirational stuff. And it's why broadcast has always stuck with me, and it's why I made a career from it, because it's absolutely fascinating. Anyway, continuing from this, you can see I've been reading the book, I've learned some theory, and now I need more equipment. So TVs are everywhere. People were throwing them out in my teenage years, ones with valves in and old technology, and they were upgrading because there was a lot of Japanese TVs coming out at that time. This stuff was in abundance. Have you heard of skip diving? Is that still a thing? Well, I was out with my friends. Dumpster diving is what they call it in America, and it basically means going to the junk where people throw things out and pull it out again and reuse it or fix it. So I ended up investing in this exact oscilloscope. You can see how ancient this thing was. The bandwidth on this was 50 megahertz. That's going back to, I purchased this when I was 16 and I'd saved up. It was £100 back then, so you can imagine that was pretty expensive. Another funny story about it is I actually dropped it on the way home. But I'd broken it. Turns out that one little transistor had fallen out of its nice little package, and I was able to push it back in, and it worked. I was very relieved. But you can imagine having paid £100. I'm a teenager who's saved up for weeks to get this thing, and I dropped it. So be careful with these old things. Anyway, you don't have to worry about that now. You can get one of these Picos, and if you drop that, it probably won't do a thing to it. But that's what started it, 50 megahertz bandwidth. From this, developing on with those consumer products and broadcast receivers, I moved on to video recorders, more reading. I can't tell you how important it is reading about things. I know that you've got YouTube and all these other sources of information, but nothing beats reading. And that's what did it for me. Reading, studying, and then applying it to some practical work, which I think you're doing that in your own little community, yeah? Go ahead.
Yeah, I totally agree with this. Like you were reading books, so it's really like modeling in engineering. So with limited information, so we can compare reading with other like videos for
Yep.
reading. So
It's a complement.
Yeah.
I think it's complementary. But nothing replaces the reading and reading papers. Even if you've got them audio to, text to audio, and you just like listening to them, and you find that a better way to do things. If you don't like reading, you can do that. But the key thing is learn something and then investigate. Now, the beauty of the electronics that I grew up with is it was far more accessible. You can see that being able to trace a signal path is a lot easier 30, 40 years ago than it is today. Have you noticed if you open a modern consumer product or any electronics for that matter, is it easy to find a signal path? Have you noticed that? No. Yes.
The fun one is when you think, oh, just look up what the IC is and the sound kit that the serial number.
That's another issue. Everything in those old TVs when I was growing up was accessible. I could easily source parts. Everything was readable and everything was repairable by the user if they'd done a little bit of reading. Now, there have been recently, I know this is a bit of an aside, but it's valuable information. There are things called right to repair. Have you been hearing about these? I agree with those things. I think that if you want sustainable economy and you don't want to create lots of waste, it's better to repair things. However, This is not good for the corporations and making profits because they want to sell you new things.
Yeah.
So repair was much easier. I could see the full signal path. There was no firmware upgrades back then. It was all implemented in hardware. It was easy to fix. It just required some study to understand what signals were propagating in what components, where they were heading. You could find the problems and fix them. These were fascinating, were video recorders, because they were electromechanical. So you also got experience in mechanical and servo control groups as well. Yes.
So if anyone doesn't know, there is actually a repair cafe that goes around about every month in the makerspace in the Royal Library. So if you want stuff to try and fix, go there.
Yeah, plug that. That's a great thing. The repair cafe.
Yeah,
and where is it? Edward Boyle Library.
Yeah, Edward Boyle made for space on the ground floor.
Like 1 to 4 p.m.
Mm.
Yeah, something along those lines.
Sorry, do you mean like, Craig, do you mean like there is a organization in the
It's just a bunch of people like you can sign up to go down there and try and
So they're
fix
all-
stuff.
are they going to try to teach us how to fix them, or?
And if there's someone there that's willing to try and teach you, yes, but like if you have a broken laptop, like it subjects something it needs resoldering, you could take it down there and see if they have a spare, and someone will try and fix it for you.
Wednesday, what is the time, the location?
You'll have to double check the files. I'm not sure, but more likely, yes.
Pretty sure it's something like 1 to 4 p.m. or something like that.
Apologies for derailing.
No, it's all right. I also recommend that you make use of the Helix as well, especially with your projects. Those of you that are going to be doing final year projects or even projects at different levels, you should definitely get involved in that. There's a lot of 3D printing. They run some courses down there. There's vacuum forming. I don't know if they've got soldering capability down there or not, but they've certainly got quite a lot of manufacturing capability. So make use of that. Fantastic. So part of what I'm trying to say to you is that you need to be proactive. It doesn't matter when you start discovering or when this, and is it fair to say that most of us here have had a moment where we discovered something in electronics or in engineering in general that switched us onto that? Has that happened to most people here? Something has happened. There's a moment and it triggers something. And that's what I'm trying to inspire you with, is that moment you need to cultivate it, because that's usually the guiding force in your career. So leading on from that, I got into magazines. Now there's lots of online resources. You know more about that than I do, but I started again reading and building kits. This was one of the kits that I built when I was getting into more advanced circuitry, and it was an optical link using PWM way back in the 90s. Quite an advanced thing. It's a fiber optic link, a transmitter and receiver circuit. I built this, I started testing it, modifying it, using my oscilloscope, getting more advanced test equipment like signal generators. I had multimeters, and it's still going on to this day. I'm still acquiring equipment and still doing work myself in my own time, not just using university equipment, but my own equipment. So you have access to far more tools than I would have, or an equipment that I would have had as a teenager or even in my 20s or doing my degree, far more. We've talked about nano, the nano VNA, the tiny SA, all of these other signal generators, the Pico oscilloscope that I've talked to you about. You have access to all this. Software-defined radio. Craig and I, we've talked about the software-defined radio. Massive amount of equipment, incredible capability. This did not exist that long ago. Not that long ago, but none of it was available. So it was a signal generator to me, RS signal generator back in the 90s. This was out of my reach. Now, nano VNA, what is it? 100 quid? 70 quid? 50 pounds. And you have access. Is it up to 3 gigs or have they gone beyond now? Is there a 6 gig? I have a 3 gig one. And I've tested it. It actually works. Maybe they've reduced the amount of those going out. 3 gigahertz. Now, are they the same as the test equipment that you use in industry? No, of course not. But for indication only and giving you a rough idea of how circuits work, it's incredible. So there's a lot of cheap test equipment to really get you enthusiastic and building projects and developing things. So Once I graduated, I went to Huddersfield, did a degree in electronic and electrical engineering at Huddersfield. It was a sandwich degree, so I also did some work experience. But after that, I went into RF and microwave, specifically at Filtronic Components. Now, does anyone know the history of Filtronic? Well, you should do, because it's from here. It's from Leeds University, and it was set up by Professor David Rhodes. And if you go downstairs to the foyer, there's a glass cabinet there, isn't there? Have any of you noticed the glass cabinet near reception?
I think it's not in the reception. It's in the reception. If you go there and turn right, so
It's near the lift and reception, if you like. But there's a glass cabinet, and it has textbooks in it. Those textbooks are authored by professors from the university or associate professors from the university, from our school. And two of the books are authored by people who worked at Filtronic. One of them is David Rhodes, and it's a filter design book. And the other one is by someone called Ian Hunter, who also worked at Filtronic and wrote a complete history about Filtronic and how it was born. So this particular company is spun out of Leeds University professors. And a number of people who graduated and specialized in microwave and RF technologies went to work for Filtronic. I spent 3 years there. And my speciality while I was there, amongst other things, was suspended substrate strip line, which a lot of work on that came out of Leeds by someone called, his name's escaped me, I think John Dean. His name was John Dean, and he worked at Filtronic as their engineering director. So this is actually a coaxial structure. It's still used to this day. It's a high Q circuit design technique, and it looks coaxial. So you have ground plane at the top, ground plane at the bottom. It's completely sealed. They can be hermetically sealed, so they can be used in aircraft. They can be used in ships, and they're predominantly used in defense applications. And that's all I can say about Filtronic, because it's secret is the rest of it. All right. But these were the kinds of things I worked on. I enjoyed it, but I wanted to get back to broadcast. And an opportunity came up at Pace Microtechnology. Has anyone heard of Pace Microtechnology? Pace Microtechnology made set-top boxes. They make them for the satellite receive business. So Sky used to be a buyer of those. We've also got cable set-top boxes, which I worked on, and I'll explain in a moment. And there are also terrestrial TV. So that was for TV sets and also for terrestrial receivers for set-top boxes. So I worked on those. But the revelation, I've not gone into great detail during my university studies I'd heard of it, we'd done some theoretical work, but I'd not realized the power of it at that time. It was still emerging. It's not like now, you're learning about it. Is anyone on Triple E program? Okay, Triple E, anyone doing ECE, the new computer program? No? ECE, which is Electronics and Computer Engineering. No, all right. If you're on those programs, there's a module called 3612. And on this, it's media. So you'll look at how to create JPEGs. You'll look at DVB and DVB-T systems. You'll study this. This is what the spectrum looks like for digital TV transmission. Have you heard of COFDM? OFDM. Okay, does anyone know what that stands for or what it means? Orthogonal frequency division multiplex. Have you heard of that? And then the other one is coded OFDM. Well, broadcast TV in this country uses COFDM. In fact, Europe and a few other countries use it as well. If you're in North America, it's 8VSV or ATSC, the system that's used there. It's different. And then there is another standard that's also used in, I think it's used in South Africa. It's definitely used in Japan and was largely born out of Japan. And that is ISDBT. And China also has its own standard. DBMT, I want to say it is DBMT. That's the Chinese broadcast standards. So there are many different ones, but most of them, ISDBT and the DBMT that's used in China, look like this in the spectrum. It actually looks like Gaussian noise. But that is actually a TV channel. Well, it's not just one channel, it's multiple channels. It's a multiplex of channels. So, for example, in the UK, a broadcast channel is 8 megahertz wide in the UHF band, and that single carrier has multiple TV channels in it, digitally stored in that channel or transmitted within that channel. Now, if we go back to the analog that I grew up with as a child and that I was interested in reading about, that is a single channel in an 8 megahertz bandwidth. Okay, so you can imagine the efficiency, the spectral efficiency that we've achieved now, the spectrum efficiency, because now we can send tens of TV channels in one 8 megahertz bandwidth rather than a single TV channel in our analog configuration in that same 8 megahertz bandwidth. So this represents what we call the picture carrier in analog. We have the color information or chroma carrier, and then we have the audio carrier, and you could physically see them in the broadcast channel, in the frequency domain, which is what these are. But this means nothing, does it, when you look at it? Just like noise, high-level noise, but that is co-FDM. And it has a QAM-like constellation. Put it on it. Yes?
So do you mean like this is these two pictures show the different distinguish from between the analog digital? So
yes.
you feel like analog, so it's not efficient enough, but you can easily see so which part is which.
It was wonderful. Yeah, you can imagine a young person learning electronics. This is instantly recognizable once you understand what this means. To someone who's now studying digital systems, you're all studying digital systems, you have not come from this background of understanding, well, what is it constructed from previously? How was it done in the past? This is what you see. And it doesn't really, it's not very interesting to look at. This is multiple carriers. That's just one, but this is multiple co-FDM carriers. So this is 1, 2, 3, 4, 5, 6 carriers in that spectrum. The other problems that we had with analog was that you couldn't butt them up against each other. The filters in the receivers were very poor in terms of selectivity. Have you heard of that term before? Selectivity. Yeah. So if you don't have good selectivity in your filters, the ideal is a brick wall, which is not achievable. But that's the ideal. You will actually cause interference on that receive channel. So we used to have nothing either side of these channels so that you had no what we call co-channel interference. But in the digital system, you can immediately see now we can put them side by side and we can actually very cleverly filter out interference between adjacent channels. So this is amazing. You can even have something called single frequency networks using this particular approach. So this is powerful stuff. And it was a real revelation to me. And I learned so much more about digital systems from this. Now, moving on. I'll go through this as quickly as I can. So, Pace Microtechnology. I'm actually now focused on, as a senior design engineer, on not the TV picture creation, but just on the RF side. So that spectral plot on the previous slide, I'm working on receivers, being able to find that digital channel, pass it on to the demodulators, which is in this chip, and that ultimately does the decoding as well. So demodulation, decoding, and that ultimately gives you the TV picture. So what I designed was this, and this is actually a picture of the front end that I designed while I was at Pace Microtechnology. And I was a pretty young guy. I was still in my 20s at this time. And they said, right, you can design that DI4000 front end. And I ended up designing all of the amplifier structures and splitters that are underneath these cans. There are two tuners here. Tuner 1, tuner 2. What do you think that enables if you've got two tuners? You can look at two channels simultaneously. So you can do something called picture-in-picture. That was a big thing back in the early 2000s. Being able to display a picture of what was on a scan channel, what you're sweeping through, and being able to watch the main TV program was a big deal. While I was at Pace, this also evolved into something called PVR, which is more commonly known as DVR now, personal video recorder. You could record a channel while watching another channel. This was a major breakthrough back then. So digital video recorder is what we call it now. And of course, now we're advancing to cloud storage where you don't have to do this, or the subscription services where you're just using streaming to access content. But this was the approach back then. Major leap forward. So I designed those front ends. So as senior engineer, moved on to be principal engineer, designing semiconductor, and I worked on these modules. So they were getting smaller. You'll notice that there's a theme here that things are getting smaller and smaller and smaller. This is higher levels of integration, and that's driven by semiconductor industry. You've heard of Moore's law already, right? Okay, every 18 months, we used to double the number of devices we could put on a silicon chip. That is slowing now, but it hasn't completely stopped. We're still doing some scaling, but it's slowing down. We were doing a massive amount of this. But you can see what's happening is that the complexity of these things is moving from the circuit board into the chips themselves. And that's why IC design is so critically important. And it's something that I realized when I was at Xilinx Semiconductor. And that was that this is the place to be. Semiconductors. So semiconductors drives everything. This is the tuner. This is effectively what selects one of those channels. I was showing you those separate co-FDM channels. This device, and that's where my expertise was, selects that channel. And some of these projects that you're working on in your community, you're worried about being able to select channels, right? Being able to select the channel of interest. That's what the tuner does. The DMOD extracts the digital information, and that gives you what we call a data stream, or in this case, an MPEG transport stream. And in that is the actual TV programs that you can pass to a decoder and extract the TV, audio, video, or data. So that's what I worked on there. And I specifically worked on these two devices and optimized them. Found a problem actually with this tuner and fixed it. A metal layer fix for that. So worked on chip characterization, working with design engineers to optimize the systems and basically sell at a low price with high performance. That's the key thing. Low price, high performance in consumer. So I ended up being headhunted for a company in the US in Dallas, Texas. And I went to work on something called the triple tuner, which is 3 tuners now, rather than just 2 that I'd worked on at Pace. And this was a revolution, and it ended up being taken on by Samsung. Samsung used this platform, and it rolled out into many of those. So you know how big Samsung is. Samsung is a South Korean set-top box. They're into everything electronic, to be perfectly frank. They're in everything. LG were another. QMax, this particular system that I designed and worked on, ended up being taken on by these major companies. We did try with Motorola, and we were in Scientific Atlanta as well. So Motorola was a bit difficult. There was another key supplier there called Anadigix, and they wouldn't let us in. We couldn't get that business. But this was a fascinating time in my life. I did a lot of international travel, and it was all around semiconductors. I think that most careers, if you want to get into design, it's ICs. That's the future. It's in integrated circuits. Now, I know you hear a lot about AI, and maybe some of you want to go work in the AI industry, but everything is driven, even underneath the AI. Which company is driving that? Does anyone know?
Yeah, NVIDIA.
NVIDIA. You've heard of Blackwell? The chip that they have? That's driving that industry. It's semiconductors. Yes, there are lots of fancy algorithms in there, but the semiconductors are really driving it. You take that away, there is no AI. So it's critical. And it's critical still if you're interested in broadcast or anything relating to communications, the semiconductors are key. So this was a fascinating time in my history. I got to travel. I won some awards, particularly for this design. It was very successful and rolled out into many platforms, and I got to show it off in many different places. So this is me in Philadelphia in 2008 at the SCTE show. I was also at, I've got the show now. NTSC. I was also at the NTSC show. Oh, this is the NTCA show, sorry, in Las Vegas. That's where we showed it. And that was my office and my lab in Dallas. Lots of equipment, advanced test equipment, nothing like I bought when I was a teenager, that old COSOR 50 megahertz scope. This was the latest and greatest test equipment. Millions invested in the labs. Where did that lead? Well, I did management for 6 years and I got tired of doing management. It's very tiring managing people. So I ended up moving to Austin, Texas. But before I move on, can anyone spot me in the Where's Waldo? That's the team photo from Microtune. Well, I won't waste too much time, but I usually spend a bit more time on this. There's Waldo. That's me back in 2006. No beard, more hair. If you remove it there, you can see evidence I actually did have more hair and no facial hair at that time. Right. Look at me. Right, Microtune. I went to Microtune. Oh, sorry, that's wrong. This one should be Silicon Labs. I haven't modified that. And this is in Austin, Texas. So I'll modify this slide if you want to come. But this is in Austin, Texas. And I was working on a brand new generation of chip for broadcast standard. This was actually integrating both analog and digital technologies. So the previous chips that you saw for the triple tuner were all analog. They had some register control in there using I2C. This was still an I2C device, but it had something absolutely phenomenal in it. It had DSP. We could make firmware changes and fix problems in hardware using software. And this is a powerful thing. So is any of you here doing DSP? You should be if you're on triple E route, right? So DSP is another very powerful subject that you're studying. Yeah, DSP engineers, RF engineers, yes?
Is DSP means digital signal?
Signal processing, correct. DSP. So we were able to do all of this side, all of the receiver, and you'll learn about IMQ. You'll learn about image reject mixers as well. If you've not, you can always read about them. But that is what we did in the analog side of the chip. We had these power gain amplifiers here. IQ ADCs, so that's where we digitize the signal, and then everything here is done in the digital domain. This wiped out the market. We took over a huge percentage. We stole it actually from NXP. It's kind of sad, really, because they're a European company, but this US company, they took that from NXP, and I was one of the guys that went out to Samsung and LG and many others, and we designed in this chip into their TV set. So everything under there, including the shield and connector, I designed all that. The chip itself, that was designed by a massive team, and we were involved in that as systems engineers, but this was what it culminated in. And we ended up taking a huge market share of the business in Samsung, LG, and many other TV players, and it really shook up the industry. Our competitor at the time, if you want to do some reading around it, was Max Linear. There ended up being some things called IP litigation, where they were claiming that we'd ripped off some of their ideas, and we claimed that they'd ripped off some of their ideas, and there was a whole court battle about that. Anyway, it was all resolved, and I got to live in Korea for a little while, about 3 months, working with Samsung, LG, designing this chip into their platforms, and as I said, it was a whirlwind success. However, after this, and I know you all like to think of the glamour of travel, making six-figure salaries, it's exhausting. You will get tired. Okay, so after 10 years of that in the US, I decided I was going to come back and do my PhD. So my industrial career actually ended in 2013. But what's interesting is that chip technology is still selling into the TV space because it is now what we call commoditized. Have you heard of that before? Commoditization. It means we have squeezed out everything possible in that technology space. There's no room for maneuver anymore. No more gains to be made. So it still sells in volume. But Silicon Labs, this division, the broadcast division, was taken over by Skywork, and they now sell that exact chip that's underneath there. They sell that into the market. I don't know who the major players are now. Maybe Samsung and LG still buy it. Anyway, the key point I've been trying to make here is in your career, you will enter and start doing something. Doesn't matter if it's broadcast, it could be anything. You will have technology that at a specific scale will seem like state of the art. For a few years down the road, if you stay with it long enough, you're going to find that it's either getting smaller or increasing in a highly complex way, just as we're seeing these complexities in AI. So I started in the industry with circuits looking like this, and they progressed to this. More functionality, analog demod capability in here, lots of integrated digital processing. And by the end, the last generation of chip I worked on had gone from a can about that size to something the size of my fingernail with even more capability and higher performance. This had lots of discrete components which are subject to aging, to drift over temperature, to this thing which is rock solid and will last decades probably, if it's not put under any kind of electrical stress. So that is the path that we took. There's a video here, I won't play it now. I'll send you the slides, you can play it afterwards. But this is the work I've done since then on my PhD, which is about redistribution of digital content using optical techniques. And to this day, I'm still in the lab. Still love the lab, I still love electronics. That's from age 9 to 2026. So some people, they go into sales and marketing, they want more money. I didn't like all that. I found it boring. The electronics is what I was addicted to, and I still am to this day. So have you chosen wisely? I'd say yes. You've always got options afterwards. You could go into marketing or sales if you want to make more money or become a business leader in industry. But your engineering degree, you can't beat it. You've got a very powerful degree. Okay, it's useful. You can go into many other sectors. As I've mentioned, key modules that you'll probably see on your program, 3612, you'll learn about DVB-T in there. You'll learn about how JPEG's created and something called DCT. Do you know about the discrete cosine transform? How JPEG images are created? Fascinating. This is incredible stuff. So you should love that. The other one is my new RF module starting next year. So those of you who are on Triple E will see that. We also, as William pointed out on his LinkedIn, we like to arrange these trips. If you're interested in broadcast, we should be getting this one organized again for this year. However, if you've already been, leave a space for people who haven't been so that they can join. But spread the word once I get that organized. And then I'd like to say a little prize for this question here. First to get this question right gets a prize from me. The online can try as well if you can monitor. What pivotal invention's 100th anniversary is being marked this year? Anyone? Oh, this is terrible. This is terrible. It's a tragedy. An absolute tragedy.
Too busy thinking about my deadlines.
Without using any, well, those online are probably, I'm not going to look out because they have access to ChatGPT and the search engine. You are actually playing the game straight. Yes.
Television.
Yes. Does anyone know specifically who demonstrated television?
Is that guy that demonstrated?
No conferring, no looking at any of your devices. Tom? Thompson?
No.
Thomas Edison. No. I'm going to give you the prize because at least you've got television. It's this guy.
Oh.
John Logie-Baird. It was an electromechanical system that he demonstrated using a Nibcom disc, which is this thing here, which is, you notice it's got an Archimedean spiral. That was used for vertical scanning lines, whereas the scanning line I showed you is horizontal scanning line. Okay, this was a vertical scanning line system. You should read about it, but there's another interesting thing about John Logie. He set up, or it resulted in the setup of something called the Royal Society of TV. Do you know where that was born? London. Right here. And there's the plaque, and I even wrote a little piece about it on LinkedIn, which you can search for. Did anyone read that here? Did anyone actually read my piece? Shame. Shameful. This is what I mean about reading. Stop doing ChatGPT, or well, use it as a, not for your assignments though, because you get in big trouble. Use it to complement things, use YouTube to complement things, but start reading. You've probably walked past this plaque. If you go out of the Bragg building through the revolving door and you head towards the Great Hall, do you know where I mean there? You go past the chemical block and there's a little tunnel, isn't there? Well, before you get there, that is the old electrical engineering school. And this plaque is actually on what is the media and communications building. And it's the Royal Television Society, founded here, 7th of September, 1927, a year after John Logie Baird first demonstrated electromechanical TV. And he gave a lecture here in the university. That is how closely linked, and how you'll find as engineers. You'll also find when you become an engineer in industry, just how interconnected we all are. I was shocked when I found this out. I had no idea that we had this connection to John Logie Baird. So TV is actually linked directly. Its birth is directly linked to Leeds University. So there's a bit of history there. Okay.